Hello, thanks for coming. So I'm Phong and I'm from University of Amsterdam. So, I think that, you can guess from the title that my work is to apply deep learning to dependency parsing. So firstly, as we know that estimating probability distributions is the core issue in modern and data-driven NLP models. And thanks to the definition of probabilities, so normally we use counting as a standard method for estimating probabilities. And to overcome the problem of that data sparsity, we need smoothing techniques. However, we found that there are two serious problems. The first one is that successfully using those techniques turned out to be an art, because actually we need experts' knowledge and also skills to tune the parameters and also to come up with a very good list, backup list. And the second problem is that we need large count tables to store events and also their counts. And recently, thanks to the rise of deep learning, neural network become an alternative. So to do that, firstly, we need to represent events in a vector space, and then we use a softmax function to estimate probabilities. And in the literature, we found that there are many remarkable examples. The first one for linear structures, for example, we have, an array of tokens and an array of words. There are recurrent neural networks can capture very long histories. And a very remarkable example is the recurrent network language models proposed by Milokov. And the thing is that those models have very compact size and they surpass standard n-gram techniques. And for hierarchical structures like tree, there are two challenges. The first one is bottom-up discrimination, and Sockers and colleagues at Stanford proposed the recursive network architecture. And a remarkable example is their neural network tensor model, which is now nearly state-of-the-art model for sentiment analysis. However, for the second problem, the top-down generation, for example, we have Ensner's model for dependency parsing and Collins' model for constituent parsing. To our knowledge, actually, there are no existing neural network architecture that can help us process top-down. So this is the start of our work. Okay, so this is the outline of our work. Firstly, we introduce a new network architecture. We call it inside-outside RNN. And then we introduce a new generative model. We call it the infinity order generative model for dependency parsing. And then we introduce how we can use the IOIN to estimate the model. And finally, we will show you very promising results. Okay, firstly, how we can handle the top-down generation process. Let's go back to the recursive network. So now we have a sentence and we have a tree. So for each internal node, we compute a vector representation to capture the content of the phrase that the node covers. So here we can use a network which Socker calls recursive network. So firstly, we compute the vector representation for the phrase x and y, and then we compute the vector representation for the whole phrase x, y, z. And actually, this process is bottom-up. And now, how we can handle the top-down process? We just simply, the idea is very simple. At each internal node, we use two vectors. The first one we call the inner representation to capture the content of the phrase. And the other vectors we call the outer representation to capture the context of the phrase. So we found that actually to compute outer representation is very easy and efficient. So first of all, now we have the outer representation for the parent node, the root node P2, and we know that the context of a phrase it's a combination of the context of its parent and the content of the phrase of its sister. So that's why we can compute the outer representation for the node yet as a function of the outer representation of the parent and the inner representation of the sister. And actually, we can do the same thing with P1, and we go down to Y and Z. So you can see in the graph that information is allowed to flow not only bottom up, but also top down. So actually here we can handle both bottom up discrimination and top down generation. Okay, so we have the model and we want to test our model. So here we pick up, very challenging problem, and that's the dependency parsing. So firstly, we should start with the answer generative model. So first of all, we need to parse the sentence mice love trees, and we start at the root node here, and this is the property to generate the whole tree. And actually, at this stage, the property is the property generate the root node. And firstly, we generate the dependence for the root node. We generate the token love, and here we multiply the previous property with the property generating the token love given the context that generates the token love. And then we generate the token end of children. We told that, okay, we should stop the generation story here to turn to generate dependence for the token love. And we generate the right dependence for the token love and left dependence until we cannot generate any dependence. And here you can see, this formula is to compute the probability that generates a tree. And there are two problems. The first one, how we can define the context to generate a token. And the second thing is that how we can estimate the probabilities. Okay, actually we can define the order of a generative model or context based on the amount of information that the context can hold. So here you can see, for example, we want to generate the token diversified, and we have the third order context, which consists of its previously generated sister, the head node, and the head node of the head node. And actually, to estimate the probability, we can use the count-based methods, and certainly with a very clever smoothing techniques. However, we were wondering that we can do something like crazy like this. So we want the context to generate tokens, which is, on the fragment, the whole fragment that we generate so far, and we call that context is the infinity order context. And actually, we cannot use the counting method here because the problem of data sparsity. And this is the point where we think that actually we can apply our new IORN to solve the problem. Okay, to do that, firstly, we need to distinguish two types of context. The first one is the full context. Given a tree with a full tree, and the context is actually the full context around the phrase. And the other type of context, we call it the partial context with the context to generate a token. And we use the outer representation to capture to capture the full context, and we use a new vector, we call it partial outer representation, to capture the partial context. And here we use assumption that the inner phrase can be approximated by the inner representation of the head. This assumption is very reasonable because normally the meaning of a phrase is dominated by the meaning of the head. And now given that we have the head node, and we have the outer representation of the head node and the inner representation of the head node, we can compute the partial outer representation for the first phrase. And on the top of that, we just put a softmax function to estimate the probability. And now assumption that we generate the token X, we then compute the partial outer representation for the second dependent. And finally, we generate the end of children token. And now we go back to compute the outer representation for each dependent. Yes, so In order to train this network, we use very standard techniques. We minimize the objective function, which is the regularized cross entropy. So this is actually a sum of two components. The first component is the negative log likelihood, and the second component is the regularization term. And we compute the gradient using the backpropagation through structure, and we update the parameters using other graph. Okay, now it's time to test the model. So we use various standard settings for data. We convert the tree bank to dependencies using two converters. The first one is the universal dependency tree bank tools, and we denote it PTBU. And the second one is the Yamada Matsumoto's head rules, and we denote it PTBYM. And we use the standard splitting, section 2 to 21 for training, and section 22 for development, and section 23 for testing. And all works occurring less than 3 times in the training set are tagged unknown. And for PenTreeBank Universal, we use the Go post tags. For PenTreeBank YM, we use Stanford post tagger to tag sentences in the development and test sets. Okay, in our experiments, we use 2 models. The first one is the infinity order models estimated by an IOINN. And this recursive network has 200 dimensions, and it is initialized with the Colbert and Western work embeddings. The order model is a third-order generative model estimated by counting and using Ensner smoothing methods. And actually, this model is very, very similar to the model proposed by Sagati 2009. And in the first experiment, we compute the perplexity. So just recall that, the better P estimates the true distributions of the data, the lower its perplexity is. So, the lower is better. So here you can see the infinity order model gains 7 times lower perplexity than the third order models. So that's why we conclude that counting seriously suffers from the data sparsity problem. And in the second experiment, we do parsing. The thing here is that, we believe that there's no polynomial times algorithm for parsing with the infinitive generative model. So that's why we employ 2 re-ranking functions. The first one is the generative re-ranker. So now we use the MST parser to generate a k-best candidates, and then we use the model to rescore those candidates, and we pick up the best one. And the second re-ranker is the mixture re-ranker. And actually, the final score is a linear combination of the score given by the model and the score given by the MST parser. And to optimize K, we optimize K and alpha on the development set. And firstly, we compute unlabeled or labeled attachment score. We see the percentage of tokens for which a system has predicted the correct head. And here you can see the mixture re-ranker with the infinitive order, again the highest attachment scores, and actually this re-ranker again something like more than 1% improvement over the MST parsers. And the third order and the mixture re-ranker with the third order actually gets much lower score than the infinitive order. So actually, the infinitive order performs better than the third order. And we also compare our re-ranker against the tuple parser, which is now, I believe, that is the state-of-the-art dependency parser in the full mode. So you can see here, if we take into account the label, the tuple parser outperform our re-ranker, both in attachment score and exact match. But if we ignore the labels, our re-ranker actually performs comparably with the tuple parser in attachment score, and is significantly better than the tuple parser in exact match score. So this is because we believe that because tuple parser performs significantly better than the MST parser in labeling, because the tuple parser gets something like 96% on label accuracy score, whereas the MST parser gets something like, lower than 95. And a remarkable thing we want to mention here is that using the re-ranker can boost the exact max score from 5 or 6%. So it suggests that actually, the infinitive generative, the infinity order generative model actually can capture a global structure of the whole tree. And we also compared our re-rankers against many state-of-the-art dependency parsers. Here you can see this they are state-of-the-art systems, Huang and Sa, Kuhn and Collins, and so on. And Martins et al. 2013 actually this tuple parser. And you can see, the best ones come from Bonnet and Kuhn 2012. And this system actually is a combination of transition-based and graph-based approach. And our MST plus the re-ranker ran the second best among those systems. Okay, in conclusion, so in our work, we introduced a new recursive neural network, and we call it the inside-outside recursive neural network architectures. And in this recursive neural network, the information is not allowed to flow not only bottom-up, but also top-down. So that's why we can handle both the bottom-up discrimination and top-down generation. The second thing, so for the first time, using an infinitive order model is so to be very practical. And our re-ranker performed comparably with state-of-the-art systems. And actually in our work, we also show that the neural net-based methods estimate the probabilities better than the count-based method for top-down generation. And actually you can download our show code at GitHub. And to finish my talk, I borrow the title of Baroni's paper, Don't Count, Predict. I know that, this slogan could be very controversial, but we believe that we nearly, approach this conclusion. Thank you.
Questions?
Hi. Have you looked at how it performs for certain types of sentences with your approach versus other systems? For example, did you look at sets of sentences with conjunctions, which are typically the hardest ones to get right?
You mean if I look at detail and do something like data analysis, something like that, right?
Yeah. It's like
actually, no, because we haven't done that, but we're really curious about what really happened in our model.
Yeah, like for example, maybe it would perform better in certain hard cases as opposed to looking at a global test set, right? Where you have different kinds of sentences.
Yes.
Yeah.
But yes. Yeah. Actually, that's our future work, but I cannot answer the question now. Sorry.
Okay, so it's a kind of more general, maybe even philosophical question about this work, but it strikes me that if you train a neural net to somehow represent the meaning of a sentence, or depending on your particular task, you may have some labels for a sentence.
Yes.
And then one of the first things, a low level in that net, one of the first things it will do is work out, there are many ways to deal with the variable length input for sentences, but one of the first things that I imagine one of the very first things it would learn relative to the task is which of any two words in the sentence it needs to kind of connect in some way with a strong signal of information flow. So I just feel, playing devil's advocate, what would you say to somebody who says that you don't necessarily need dependency parsing when you take a neural network approach to language, because it's just going to learn as a very fundamental, rudimentary feature, which of any two words in the sentence to kind of connect in a strong way or maybe in a less strong way. And ultimately, that seems to be roughly what dependency parsing is anyway.
Yes, a very good question. And we're also wondering about that. Now normally, flash structure also maybe perform better than if we have something like tree structure, hierarchical structure like dependency parse. But we also believe that if we also take into account the linguistic knowledge, we can improve the performance of the whole system better than if we just rely on flash structure. Do I answer your question?
Hi. Thank you for the very nice talk. This is just a minor remark, not a question. I just wanted to mention an earlier work which might be of interest to you, which is called the bidirectional recursive neural network that appeared in last year's NIPS in deep learning workshop, which has the top-down and bottom-up recursive layers on top of each other.
Yes, actually, I also read your paper, and one of the review also asked about why we don't compare our system with your recursive your models. The thing is that actually, the bottom up, the two models are very similar, but they are, but the top down process of the two models are very different. So in your model, you do top down. The top down totally depends on the bottom up. First of all, the down vectors is computed based on the up vector, but I don't think that, here we want to compute the context of the phrase, and the context of the phrase should be independent of the context of the phrase. So that's why the two vectors should be independent. So that's the core difference between the two models.
Sorry, just wondering if can you say how much better? A lot better or a bit better?
You mean this conclusion?
Yeah.
Yes, actually, we based on the perplexity to conclude that predict neural network based better than the count based. So here you can see, sorry, and yes, the perplexity of the infinitive orders is 7 times lower than the third order model. So actually, if you use counting, we need very careful about the data sparsity problem. And I believe that if we use neural network, we can overcome the problem data sparsity problem, because we use the neural network, we project the event space onto a manifold. So that's why closed structures will be projected onto closed area on the manifolds. So that's why smoothing is ultimately carried out by the network.
Can I ask one more? What about time? What's the difference between the amount of time each model needs to finish the task?
Yes, that's a good question, and honestly, I want to hide this because, if we use something like neural network, the thing is that we need to compute the probability using the softmax function. If we use the very flat softmax function, something like that, so the complexity is very high. But we can use many tricks, something like hierarchical softmax or negative sampling. But return to your question, we need about 1 day to train our recursive network, and the testing speed is something like 20 minutes for 3,000 sentences. I know that it's very slow, but the thing is that we try to speed it up, and we get some process.
Thank you.
So we actually have time for probably one last question, if anyone wants.
Yeah, actually, speaking of remarks, your model is in fact learning some sort of latent state model for dependency parsing. So even though you are in the neural network style of modeling, it clearly reminds the PCFGs with latent annotations that were developed by Matsusaki and Petrov, and then Mozilla later trained latent variable PCFGs for dependency grammars. Yes. So of course, when learning with EM, you are exploiting inside-outside recursions, which are similar to your kind of representations. Yes. Clearly, the models are different because you are exploiting some nonlinearities, but it would be interesting to make those connections more explicit.
Yes. Actually, we name our models inside-outside recursive network, based on the name inside-outside algorithm, because we also do something like inside structure and outside structures. But to compare the two things, our model and the EM algorithm, it's quite difficult. I mean, it's doable, but it's quite difficult because, I mean, the EM algorithm is, the thing come up with at the each node, I mean, is latent variables, and it's just something like, I mean, only scale variables, right? And here we have something like a vector, so so that's why to compare the two models are quite difficult.